Okay, so I've got this 6.3 working energy test here. It says foundation tier, but a lot of this is going to be in the higher tier. So I'll make sure I point out which questions those are. So the first question is a nice 2 marks. Forklift truck lifts a load of 15 newtons and places it onto a 2-meter high platform. So we've got 2 meters and we've got a distance and a force. So just using this is a nice easy calculation. So the work done, it gives you the formula anyway, but just in case it didn't, we're going to cover RW. So W equals F times D. We've got 150 times 2, which is 300 joules. 2 marks, shouldn't be getting that wrong. Give one reason why the forklift truck uses more energy than required to lift the load. Well, I've said the energy required to operate the lifting gear, and you're going to lose some as like sound, and you're going to use a little bit as heat. So it's not going to use all that energy into the lifting because some energy is wasted. You can think back to when we did foundation and we did all the energy transfers, useful energy, and then the wasted energy. Well, it's the same principle. It's not going to use all. It's going to take a certain amount of energy to lift that, but some of that's going to get wasted as heat and sound and other things. Question 2 is a 6 marker. I've tried to split this up as easy as I can. So let's go through the question. A roller coaster car has no engine, so it needs to be pulled up. Let's try and focus in here. That's better. The car is pulled to the top of the first peak for the beginning of the ride, but after that, the car must complete the ride on its own. Every peak of the roller coaster is lower than before. Explain in terms of energy transfer how the car is able to complete the ride after being pulled to the top of the first peak, and why each peak must be lower. So for number 1, I've just started quite linear here. I've sort of said it at number 1, as the car is being pulled to the top of the roller coaster, the car gains gravitational potential energy. Okay, so if I bring something up, it's always going to have that potential of gravity to drop. At 2, it's going to be the maximum potential energy that it'll ever have. It'll have more than there, it'll have more than there. Number 3, it starts falling out. So as the car runs down, the potential energy is converted into kinetic energy. Remember, potential energy is the same as kinetic energy. It's always going to be equal, but there's always a transfer. So you can think of it as horizontal and vertical. So it's getting turned from potential now into kinetic, into movement energy, even though it's still sort of vertical. It is. We say that it's always equal. So if you just remember that kinetic energy is the same as potential energy without having to go into it too much. So that is transferred to kinetic energy. But some of it is now lost as sound and heat due to frictional forces, or resistive forces, we say. Remember those energy transfers. But what it's going to do, it's going to come to the bottom, and then it's going to go up this bit because it's got momentum. And we don't talk about momentum so much in this spec. But the kinetic energy is converted again, once it goes up here, into potential energy as it climbs the incline. Again, resistive forces such as friction and air resistance cause the energy to be lost as heat. So in each one of these is going to keep repeating. The total kinetic energy of the car is going to be lost. So each peak must be lower. There's a good example online whereby a teacher holds like a bowling ball or a mass in front of his face, and it's a swing. If I just draw that for you. So if you've got the guy there and he's standing there, and then you've got this sort of ball, like a bowling ball, and he holds it close to his nose, and then he lets go. He lets go, and this ball will swing, and he doesn't move at all. And it just goes to show, he's trying to demonstrate that that ball will never really gain that much energy. It will never come back further. So he's willing to put his face on the line for the experiment. So this ball will swing. It will turn it kinetic energy. And then at this point, when it's up here, it will gain but it will turn back into potential energy, and then it'll swing back, but it will never go as far as to hit his nose. So he's really confident in that experiment, and it's because it's never gonna pick up energy. The only way it can pick up energy is by applying a force to it if you push it. Now, if there was someone this side pushing it, then yes, it might. And if there was any energy applied here, then yes, it could take it up to the next peak, but it will always lose energy at each point. This is a higher question. Quite a long question, as you can see. There's a lot involved in this, so I'm going to open it up. So, one of the world's tallest roller coasters has an initial peak of 140, and I've kind of drawn that there. After reaching the top, the car first falls to a height of 50 meters above the ground before it continues its journey. So it's going to have that energy remaining. So the energy that it's got up here as potential energy, it's going to turn into kinetic energy, but it's going to have some left because it's not used all that distance. And I think that's what we're going to find out, how much energy we got there. The mass of the car is this. Use equation on page 2 to calculate the theoretical maximum velocity. Now, it's after a speed there of the car after this first fall, which surprised me a little, but we will see. So the only ones that we use in this spec with velocity is v minus u over at. Well, I haven't got an acceleration anywhere because I've written down what I've got there. I've got a mass, I've got a distance or a height, and I've got gravity. But I haven't got acceleration, I haven't got time, so it's not going to be that one. The other one I've got with a v is kinetic energy equals half mass times velocity. Now that looks good because I've got a mass. We want the velocity, it's just kinetic energy I haven't got. Well, because I know kinetic energy is equal to potential energy, I can use potential energy, mgh. Now I've got my mass, I know my gravity, and I know a height, so I can calculate that straight away. So 1200 times 10 times 90, because remember the height is the distance between, so it's going to be 140 minus 50, it's going to give me 90 meters. And that is going to come out to be, let's have a look, 1, 2, 3, 1, 2, 3. So that's 1,000,000 and then 80,000 joules. Awkward to pronounce, but that's the figure I get. Now I can use this, because potential energy is the same as kinetic energy, I can use this, so I know my mass, I know my kinetic energy, I can find out v squared now. So v squared is going to be equal, so I'm covering my thumb, to ke over half m. Well, my ke is that figure there, that 1,080,000. My mass is half 1200, which is 600 essentially. I've done it all in one, which comes out to, so v squared is 1,800 meters per second, but that's v squared. We've got to get v on its own, and to do that, we need to use a scientific calculator, and we need to apply this. So let's put on. So if you look, where am I looking? At this button here. See, there's like the square root and then a little box. If I do that, press that button, and then 1800, and it comes out to be 30, and then the square root of 2. But to get that into a number I can use, is 42.204 meters per second, sorry. And that's how I get that. So quite a bit of work there, but it is worth 4 marks. And again, this is a higher question. Discuss whether or not this theoretical maximum velocity, so whether or not this velocity depends on the mass of the passengers. Well, like I said, kinetic energy equals potential energy. Therefore, half mv squared equals mgh. Now, if I change either of these masses, if I increase that one, this can be increased. If I decrease that one, this can be. So they kind of cancel out. So I've said no, it doesn't affect, because the mass is always cancelled out. Whatever the mass in here is going to be the mass in there. Whichever mass I'm using is always going to be equal to the other mass. So it's always going to be cancelled out. In practice, the car reaches a velocity of 37, which is a fair bit slower than the 42. After the first fall, the length of the track on the fall is 100 meters. Use the equation on page 2. So we're calculating now the resistive force, not the force of the car falling, but the resistive force, because it was theoretical force, or sorry, the theoretical speed is that, but actually it's that because we lose quite a bit as friction, heat and sound. So now it wants me to calculate this new force, a resistive force. Now, I've got FMA to calculate force. Well, I haven't got an acceleration. I've got a mass, but I haven't got an acceleration. Now, I could go down the roads of V minus U over AT, but, you know, when we start looking at these initial speeds and final speeds, it's going to get confusing. So I opted to use the other one with force, which is energy or work done over the distance, because I've got a distance there. Okay, so even with that V minus U, I still haven't got a time. So it's this equation. It's going to be EFD. Well, I haven't got an energy to get my force, so I've got two unknowns. I only know my distance. I know a speed, and I know my mass. So because energy, all energy is the same, whether it's kinetic energy or gravitational potential energy, I can use what I've got to calculate energy. And this is what I've got. I've got kinetic energy here is half mv squared, where I've got a speed, I've got a mass. So let's go for it. Let's calculate my kinetic energy. So I've done it there. You can see that I've got 37 squared, which turns into 1,369, which when I half it becomes, this is my new energy at 37 meters per second. But this is not the one we use, because this energy is at, so you can see I've taken it down, at 42 meters per second, or 42.4 meters per second. This was my energy. And I should have put a joules in the end there. We calculated it up there. Yeah? That was at that speed. At my new speed, I've got a different energy. At a slower speed, there's a slower energy. So to find that frictional, the resistive force, I need to take one away from the other. My resistive forces are the difference between them, because this energy is being put in to make it move. I need to find the energy that's being lost, and to do that, I take one from the other. So I come out with a new figure of 258,600 joules. Lost is heat and sound due to friction and air resistance. Got my energy here to plug into this formula now to find force. F equals E over D. My energy, my friction, my resistive force, my resistive energy goes here. My distance is 100, and I come out with 2586 newtons. That is my mean resistive force. So quite a bit to get there, but another 4 marks. So this paper carries, this side alone carries 10 marks. On to the last question, and again, another sort of tough one to get your head around. It says, describe how Newton's third law applies to a rocket taking off. So I've done a little diagram. So here's my rocket. It's going to take off. It needs to be, it needs some exhaust gases. Now, the one common misconception is when a rocket takes off, we always think that initially it's from the ground, it's reacting against the ground. But if that was the case, it would only get to a certain height and then it would come back down. The main thrust is caused by the force on the exhaust gases, because they continue as the rocket rises. So the third law states that we've got equal and opposite forces. So the amount of force that I push on the table is the amount of force that table's pushing back on my hand. And the same applies with the gases and the rocket. So I said the rocket exerts a force on the exhaust gases, and the gases exert a force on the rocket. So that will cause the rocket to rise, because it's always bouncing. This rocket is always bouncing off these gases, which is going to make that rocket accelerate up. Like I said, equal and opposite force causes the takeoff. That was 2 marks. This one, quite a bit of reading. So let's have a look. I don't even know if I can. So the Cassini spacecraft with its Huygens, I'm going to say for now, probe was launched by a rocket was launched by rocket in 1997 to study one of Saturn's moons. On the 14th of January 2005, the Huygens probe landed on the moon, Titan, and was slowed down by a parachute which opened 120 kilometers above the surface. Okay, so there's a bit of information. I've got this information here, which I'm not going to go into yet. Let's have a look what the question wants me to do. Discuss the acceleration. So I'm going to be talking about acceleration on the rocket at its launch, including your answer. So these are the two things to include. The calculation of the initial acceleration. You need to be finding the acceleration. Hint, consider the weight. I'm going to line that because that's important as well. And then an explanation to the way the acceleration changes as the rocket rises. So that rocket is going to increase in acceleration as it goes up. Ignore the effects of air resistance there. So where do I start on this? Where do I start? Well, it's asking me to find an acceleration. Now we deal with two accelerations. We deal with v minus u over a times t. We haven't got a time, and my initial velocities it's not there. It's not going to be this one, just by looking at the information. FMA, well, I've got an acceleration there, so I can use this. Have I got a mass? Yes. Have I got a force? Yes, I've got some forces. So let's write down what I know. Now this is done in standard form. Now just to show you standard form, because it gets quite confusing, you see this and you think, I'm not going to attempt this because I just don't understand the numbers. 9.5 times 10 to the power 5 is quite easy, really. If you've got a scientific calculator, if you did 9.5 times 10, and there it is there, times 10 to the power 5, compressive quote, it's just 950,000. Now, if you count the zeros, or count anything after the decimal, so it's 9 point, and then if we got 1, 2, 3, 4, 5, can you see that? 1, 2, 3, 4, 5, including that 5 there, zeros after. So there's 4 zeros in that 5, because this 5 means anything after this decimal point is going to be the rest in zeros. I've done the same with force. Look, have I got a force? Yes, I have. I've got the engine thrust on the rocket at takeoff, 1.5 times 10 to the power 7. Again, that's easy to do. I got 1, and then I need 7 figures after, including my 5. So 1, 2, 3, 4, 5, 6, 7. So that's a number I can kind of deal with and get my head round rather than using all these numbers all the time. So if we look at this diagram, what it's really asking me is to find out the acceleration. But I need to know, I've got a force going up, but what's my force coming down? Remember, it says consider weight. So it's not just going to be 1.5 and nothing reacting on it. Now, if it's going up, this arrow is likely to be bigger. So let's calculate my weight. So the weight is m times g. So I've put my figures in there. So I've used this mass times the 10 for gravity to get it off the Earth. And I've come out with 950,000,000 newtons. In standard form, 9.5 times 10 to the power 6 newtons. Now that gives me my force going down. So 9.5 times 10 to the power 6. But I need a resultant force. The resultant force is the big one, the little one take away from the big one. Because I need to calculate that little force that's making it accelerate up. So I need to take the big one, which is the one, so the arrow going up. Because it's going up, it's always going to be bigger. I need to take the little one from the big one there, which is 550,000,000, or 5.5 times 10 to the power 6. I might have added too many zeros on there, what I was saying. But that is now my resultant force. I've got my force. I've got my mass. I can find my acceleration. So I've said A equals F over M. That's my F, my resultant force, 5.5 times 10 to the power 6. My mass is 9.5 times 10 to the power 5. I come out with a speed, acceleration of 5.789 meters per second squared. That's going to get me around about 4 marks, 3 to 4 marks, just doing those calculations. Second part says an explanation of the way the rocket accelerates during. Well, I've said the acceleration will increase because the fuel is getting used up. This causes a decrease in the overall mass. If you think that the mass of the rocket has, so the stuff in the rocket has the fuel in it. As the fuel gets used up and turned into gases, it's going to lose mass. Therefore, it's going to lose weight. So if that weight decreases, as this number gets smaller, the force is going to increase. Therefore, the acceleration is going to increase. And then the last question there, calculate the loss in gravitational potential energy. This is a higher question. This was foundation, by the way, a really hard foundation question, because all of those equations we use in foundation. This equation we use in higher. Calculate the gravitational potential energy, so GPE, in the Huygens probe during its descent. Remember, that's why that was there. Sometimes these questions you have to throw you off. They put a lot of bump in you just to throw you off, like the years and things like that. So this one's quite straightforward. I've got my mass of the Huygens probe, which is 320 kilograms. My gravitational field strength is 1.35, which I put there. And it said the parachute was 120 kilometers. Now, this height has always got to be in meters, so I've converted that there to 120,000 meters. And then I've just used my equation, mgh, and I've come out with that answer. And that was the end of the paper.